So we will start at 6 5. We will wait for other students to join, and then we will be continuing our session. So, good afternoon, everyone. I'm Prashil, and here we are learning advanced thermodynamics and molecular simulations. So, this is our week 3, and here we will be discussing the assignments that has been already submitted. So, it would be useful for you to work upon the problems to get the solutions of the questions that were there in the assignment. So, the recording of this uh, meeting will be available on the YouTube channel, and the links for other sessions will also be shared with you through the Google Sheets. Okay, so we had started with the advanced thermodynamics and simulations, right? And then we studied, okay, why we are learning this thermodynamics, right? We started with the basics. We started with the basics of thermodynamics, and we were using some advanced methods, for example, StatMech, right? We were just giving it a mathematical framework to the thermodynamics that we have already learned, right? So there we saw, for example, I have a system, right? It has some chemical in it, right? And this system is not exchanging energy with the surrounding, and it is also not exchanging mass with the surrounding, right? So if mass exchange is zero and if energy exchange is also zero, then such sort of systems were called as isolated system, right? We used to call them isolated systems. So this we already learned, but then when it comes to the statistical mechanics, we have given it a mathematical touch. For example, if the mass transfer is not happening with the surrounding, this is my system and outside is my surrounding, right? This is my surrounding. Then mass transfer is not happening. That means number of molecules are constant. Similarly, energy is not exchanged, right? Therefore, energy is also constant. And then volume of the system is also constant. So such systems are called as NVE systems. NVE systems, right? Where number of particles, volume, and energy of the system is constant. So similarly, it happens for open system. It is the case for closed systems, right? So depending on the system that is under considerations, we can choose a particular type of ensemble, we call it. So this is called as ensemble. We need to first look after what is changing and what is constant, and depending on that value, we will have to see whether it is NVT system, NV system, or any other system. And then accordingly, we use the equations that are there for the particular system. For example, when it comes to NVE system, isolated system, you know everything is given in terms of entropy, and entropy is something that defines the progress. When it comes to NVT, you know this is a closed system, and for this closed system, delta F is equals to kb t ln of q nvt. Q nvt is a partition function that we have discussed in the class in detail, right? Partition function which has information about system, and based on that you can calculate the things. Okay, just a minute. हाँ बोलो कुमार. मैं 7:30. हाँ हाँ. 7:30 के पहले नहीं मिलेगा. हाँ ठीक है ठीक है. मैं आ गया हूँ. और इनसे सर्टिफिकेट है हमारे पास, साइन के डॉक्यूमेंट भी है इसके पास. ये एनपीटीईएल में बच्चे हैं. पढ़ाना है उनको ऐसा। हम्म, ठीक है। So there was an urgent call, and what we were discussing? We were discussing how to represent a particular system using the statistical mechanics, and then we have a something called as free energy, which defines whether the system will go into that state or not. Similarly, for example, I am having NPT system. Then in those NPT systems, it is something called as delta G, and that's where we say delta G is equals to KBT ln Q NPT. So whenever pressure and temperature is constant, for example, the reactions that are happening in our surrounding, temperature and pressure is constant, and for those systems, it is the Gibbs free energy that defines whether the system will go into particular state or not. And minimization of Gibbs free energy is something that will tell the spontaneity of the process. Correct? So this is how we have defined those things. Then we have talked about, okay, for any system we have a phase in which we can distribute energy into the particles. So we talked about energy distribution in molecular system, right? So we talked about energy distribution in molecular system, right? And there we had a Gibbs distribution, right? The distribution, what it was saying, Boltzmann distribution, I should say, which tells you how many number of molecules will be present in a particular energy states, and we have related that using a formula. Nj divided by Ni is equal to, there was a formula which was telling you, okay, the relation between what is the interaction energy, that is what is the change in energy from one level to other, and then there was thermal energy, right? So ratio of these two will give you probability, right? And there is some pre-exponential and exponential term is there. So this is something which tells you whether if I am able to achieve a particular energy state or not. Its probability can be calculated using this Boltzmann distribution. Correct? Then using this, we went to multiple systems, as like I said, NVE system, then we had NPT, NVT, right? And for all those systems, we calculated what is the W, right? And W was given as n factorial divided by n not factorial, n1 factorial, and so on, right? So this is for the simple system, but we can have multiple complexities depending on the controlled variable, right? Controlled variable will decide these things. And then we wanted to maximize W. We wanted to maximize W, right? A W maximum will give you will give you the equation for that particular system, right? So this was the thing that we discussed previously. So now we will be solving some of the questions that were there in assignment, right? So that were there in the assignment. So the first question that was there in assignment was, which law of thermodynamics defines the arrow of time? Which law defines the arrow of time? So take your time and think about it. What was the answer that you had given? So this was discussed in first class. There we were talking about multiple laws of thermodynamics. Right, so the answer is already known to you from your undergraduate studies, that it is the second law of thermodynamics that defines the arrow of time. Why is it so? Because we know zeroth law. What was the zeroth law? Zeroth law was telling you the definition of temperature. It was talking about equilibrium. If I am having a system A which is in equilibrium with system B, right? So there has to be something common in between A and B, right? There has to be something common between A and B, such that if C is coming in contact again, right, that property will be constant in this case also. So it was telling you that it is the temperature that is common when we evaluate the system, right? It was the temperature between two systems that is constant when these three systems are subjected to equilibrate over the period. It can be anything. For example, I have a Coke bottle and I have taken this Coke bottle out from the fridge. There were three bottles, for example, and I'm keeping all of them in room temperature. Now you can consider A as a Coke bottle, B as water, which is normal water at room temperature, and C could be coffee, hot coffee. You keep all these in room temperature, right? What will happen? All of them will come to an equilibrium state where temperature of these systems will be constant, right? They will be exchanging energy with the surroundings so that the temperature is constant. So this is the definition of temperature. So system A is in equilibrium with system B, and if system B is in equilibrium with system C, then A and C will be in equilibrium, right? That means the temperature of system A and system C will be same. So this was about zeroth law. Then first law, what it was telling you? It was telling you about the energy conservation, where delta U for a particular system is equals to Q plus W, and depending on the sign of W and Q, the equation can be Q plus W or Q minus W. Generally it is Q plus W. Whenever we are adding energy into the system, it is positive. Whenever we are doing work on the system, it is positive, and that is what we say, it is Q plus W. So this tells you the conservation of energy, which says that if a system is, is going from state 1 to state B, what is the change in energy? What is the change in energy? And in an isolated systems, we know the change in energy is zero, correct? That means energy is not changing. So that means if energy is not changing, what is something that drives a process to happen? What is that thing? If you want to get those things, then you need to understand something called as direction of a process. So for example, in first case, when we took Coke bottle out, right, at that time the temperature decrease, the temperature increase, right? So temperature increase when we kept it at room temperature increase. Why not the temperature decrease? That means it is telling you that energy is transferred from system A to surrounding. Correct? So there is some direction, and that direction cannot be defined by entropy because it says entropy is constant. Correct? Entropy is constant for an isolated system, and if you consider universe as an isolated system, if a system is having constant energy, right, constant energy, that means whatever the process that are happening, how and why they will happen, it is because there is something called as entropy. That entropy keeps on increasing, so delta S is greater than 0. Delta S is greater than 0, and therefore we can say it is something that tells you the direction of the process, right? So question number 1. Now question number 2 is there. Please try to solve this. We will be discussing this in a minute. So let us solve this question again quickly. Molecular simulations can be used. So why molecular simulations is important? That's what the question is asking. So the question is why molecular simulations are important. These are important, for example, to determine the equation of state. In class we have studied in detail using thermodynamics, right? We took ideal gas, and there we said, okay, for that ideal gas, the energy is proportional to the velocity is proportional to the temperature, right? Root means square value we used to take, right? So this is what is square value of the velocity, and this is what is temperature. And then we also defined that it is decreasing with respect to the mass. So if I'm having a bigger mass, right, and if I apply some temperature, it may not lift. But for example, if there are gases which are very small particles, and if I apply the temperature, the gases will move, right? So depending on the mass, it is also changing, and it is inversely proportional, right? So that's why we have used these two analogies, right, to get equation of state, and that was PV is equals to nRT, right? PV is equals to nRT. Similarly, we can take some other system instead of ideal gas. We may have some approximation, for example, two atoms cannot penetrate, and depending on that, we may be having always there will be some volume that is being left which cannot be accessible, which cannot be accessed, right? If it is not accessible, then in that case we have to use this condition over there, right? And we can get equation of state. So that means molecular simulation, or I should say statistical mechanics, can be used to determine the equation of state. So this is first. What about second? Determine the thermodynamic behavior, right? Yes, molecular simulation can be used to determine thermodynamic behavior. For example, I have a I have a system in which I have water, and this is a hot water which was there at 25 degrees Celsius, and I have changed its temperature from 25 to 30. So these studies can be performed using molecular dynamic simulation. We will change the temperature, we will calculate the properties at 25 degree, we calculate the properties at 30 degree, and we will see how it is changing, how the properties are changing. You can calculate something called as free energies of solvation. If I want some atom or some molecule to be inserted in this water, then what is the energy that is required? So those sort of things are the thermodynamic properties. So these properties can be calculated using these properties can be calculated using molecular simulation, how the changes that are happening, right? So this is being used to determine the thermodynamic behavior, to determine the physical changes that are occurring into the process. Yes, that we can see. For example, I have a system which has oil and water mixture. Oil is there and water is also there, which is in mixed state. What will happen after a certain time, if you let the system, or maybe you can increase the temperature, you need to give the heat, and because of it, what will happen at the end, you will be having clear separation between oil and water. That means we can use molecular simulations to see what and all physical changes that are happening into the system, physical changes. We have a mixture of gases instead of having oil and water, then what will happen, we can put membrane in between, and we'll see what and all gases can penetrate through that membrane, and what is the efficiency of separation. So those sort of things can be performed using molecular simulation. So it is used to determine the physical changes that are occurring in a process. What else? What else can be done? See, it is saying which is the best material for application among various candidates. This is also something that can be done using molecular simulation. Why? For example, if I want to mix oil and water, then I need some third component at the interface. Or if I want to separate an oil and water, then I need third component which will separate two things. Correct? So I'll try and do molecular simulation, right? So those are called as computer experiments. I can do computer experiments and screen best material out of available. The project that I did as part of an internship, it was about finding out best absorbing material for a surface. So there was a surface, and if I want to stop its corrosion, prevention, right? If I want to prevent the corrosion, then in that case I will try to simulate, or to do computer simulation of multiple molecules. For example, I have hundreds of molecules adsorbent. Those adsorbent I will test, and which one is having highest adsorption energy, that I will find out. This energy will give me, okay, the adsorption energy. If it is higher, that means that molecule has stronger interaction with the surface, right? That is having stronger interaction. So stronger interactions means it is a base coating material. So I don't need to do normal experiment over this 1,000 material. I will do computer simulations and give 10 possible best possible solutions, 10 best possible coating materials to experimental team, on which they will perform experiment, right? So it can be used to find best material for an application. For example, I had shown coating, right? correct? So it can be used to find out best material for application among the various candidates. So I hope this question is clear. Now the next question is question number 3, which tells you about energy of a particle in a constituent system. We had looked after how energy is distributed into the system, right? So based on that you can answer. So let us solve this question now. So it is energy of particles in a system. You know how the energy is distributed into the systems, and for that we saw the formula. It was W equals to, and so on, right? So here N is the energy, sorry, M is the energy which needs to be distributed, among n particles, among n particles. Among n particles. So this is the equation. This can be applicable to multiple things where we want to see the distribution, correct? So this is a distribution, and then we saw, okay, that not all the particle will have the total energy m, and not all the particle will have zero energy, and most of the particle will be having something called as average energy according to the Boltzmann distribution, right? Average energy, and the graph will look like this, where the most of the particle will be having an energy which is close to the mean value of energy, right? So it is not same for all particles, it is varying, correct? That means option B is correct. And it is keep on changing because of the collisions that are happening between the particle. There is an exchange of energy, right? If there is an exchange of energy, that means it is changing with the time, it is changing with the time. So option B and D is correct. It is varying among the particle and it is changing with time, correct? So this is the answer. So if you have any doubts in this, you can ask me. right? Then moving on to question number 4. When the system size doubles, what happens to the entropy? What factor is there by which the entropy changes? So we know that entropy is an additive property, right? And we know that S is equals to KB ln W. So if I have system S1 is equals to KB ln W1, S2 is equals to KB ln W2, KB ln W1 and KB ln W2. Right? We know that entropy of total system is equals to S1 plus S2, and if two systems are same, then in that case it is 2S, right? 2S1, that means entropy is equals to double the value. So when we change the size of the system, when we increase the size of the system, the entropy increases by a factor of 2. Therefore answer B is correct. Answer B is correct. We saw that when we double this, you can see these equations actually hold true, and then S1 plus S2 is equals to KB ln W1 into W2. Here it tells you that, see, whenever I am having multiple system, then the number of ways are basically multiplying. If I am having only one head, one coin, then I may get head or tail. Only one possibility is there. But if I am having two coins, then it is, that is double the size, right? So each head will be having each head, and each tail is also there, right? That means I will be having head both coins, head tails, then I have tail head, and then there is a tail. So you can see the possibilities has increased, and you can see each each is multiplied, right? So here there were two, and here there were two, so total is equals to four outputs are there, four output are there. So what has happened, numbers has multiplied, the number of ways were in number of ways in first system were 2, number of ways in second systems are 2, so total number of ways are 4. You can see multiplication of number of ways and addition of entropy, that is what is being observed here. And that's why when the system size doubles, the entropy increase by a factor of 2. That is question number 4. Let me know if you want to have some any clarification on this. So that's what we have discussed now. Right now, S is equals to KB ln of W. That means S by KB is equals to ln W, right? S by KB is ln W, or we can simply say S is proportional to the ln W. That means e power S is proportional to the W. That means W is proportional to the e to the power S. So answer to this question is option B, where the relation between entropy and W is given. Correct? Relation between entropy and W is given. So question number 6 is there on your screen, a bit probabilistic way, right? So try to solve this question. We'll solve this. So it says probability of picking four aces in four random picks from a well shuffled deck of cards. So we have cards, right? 52 cards are there, and for those 52 cards, we can divide them into four categories, right? Ace, spade, it's diamond, and heart, correct? So four categories are there, right? And it is asking the probability of picking four aces in four random picks. So how many picks we are making? Four picks, right? So what is the probability of getting four random picks, right? So out of 52 we are picking four, so how many ways are there? If I want to pick only one, then it is 52c1, right? 52c1, right? So this is what is 52c1. That means this many number of ways in which I can pick that, so it will come out to be 1 by 52, right? That is what is the probability, that is of picking up card, total probability, right? So here I'm asking what is the total probability of picking four cards, so which is equals to 4 I am picking out of 54, which is given as n factorial divided by r factorial n minus r factorial. That means 52 minus 4, which is equals to 48 factorial. This is what is the total number of ways, total ways in which I can pick, or we can pick four cards. This is the total probability, and we know probability of any event to happen is equals to probability of that event divided by total, right? So this is what is the total of these many ways are there by which I can get four card. So first time I'll get first four, then I'll get from 2 to 5, then I'll get from 3 to 6 and all. So four cards, how many times I can pick, what are the total number of ways, correct? Then I may start 1, I may skip 2, 3, 4 are there, and 5 is there. So these many ways we need to figure out, and this is what is given by the formula. And then from those total, what is the probability that all four cards will be ace? All four will be ace. So if I pick four card, what is the probability that it would be a ace, and it will be ace on all four cards, right? There are only four ace cards are there, right? So getting all of the four is only one way, right? Out of total number of ways I can get only once. I took four cards randomly and those are ace, so the probability is only one, so the number of ways is equal to only one, right? Therefore the probability will be p is equals to probability of that event divided by total, that is 52 divided by 4, and then 48 will be there. So if you take the inverse of this, you'll get 48 factorial divided by 4 factorial, and here it is divided by 52 factorial, correct? कुमार बोल. यस मेरे को भी नहीं दिखा ये मैं देता हूँ थोड़ी देर में देखो. नहीं नहीं फोटो निकाला था लास्ट टाइम. है मेरे पास मतलब मेरे पास होगा या फिर साइरस के पास होगा फोटो है उसका. कैटरर से लिया था यस. Okay, so this is what is the probability of that event to happen. So one out of these many ways will be the probability, and that is given by option C. So this is what is the solution to question number 6. What is the probability of getting all four cards, that is to be ace, right? It is very less, the probability is very less, and that's why you can see this small number is coming out there, right? You can also further solve this, right? That is also possible. Number will be very small. Number will be very small. Then moving on to question number 7. Question number 7. What is the probability that the fraction of heads near 0.5 in a game of 2n tosses? So these many tosses I am doing, and what is the probability of getting 50% heads? N could be any number, right? And if I increase the n as well as what we have saw, what we have seen, right? Probability of getting 50% increases, right? Close to 50%, getting the value close to 50% increases with n. Although the maximum value in that particular experiment decreases, but when it compares to the total, when it compares to the maximum, when it compares to the maximum, the probability increases. So you will be seeing the distribution like this. This is my 50% of head, 50% of head, right? So for that 50% of head, I am having all heads over here. For example, 1, that is what is fraction of heads, and this is 0 number of heads. So as I increase the number of tosses, what will happen? The probability of getting 50%, that is half of them will be head, will increase, right? It's not exactly the half value, but close to that half value. That means most of them are will be having head, and 50% most probably will be having tails, right? So this is what is the distribution you can see. Then if you increase again n, what will happen? The entire probability will decrease, but then to have 50% probability has increased, and upon increasing the number you may see like this, right? So the value at 50% will be very high compared to other values of the event, right? Other events that are happening. So it increases with increasing n. So probability of getting that value increases with n. So this is the answer to that question. That if I am increasing the number of coins, the probability of getting heads close to 50% increases. Close to 50% increases. This simple computer experiments we can also do. We can see, for example, in the class we saw, when I am having one coin, whenever I'm having two coins, three coins and all, and then we plotted this distribution, right? This distribution we plotted in the class, and there we saw it is indeed increasing with increasing n. And this is very important because it comes with the central limit theorem, right? In experiments, if I'm an experimentalist, right, I am always being asked to do the experiments multiple time, right? I need to do or repeat the experiments. If you do experiment only once, the probability of having error is higher. And if you do experiment twice or thrice, and if you are getting same result, that means you are close to that value, right? So by increasing the number of trials, if you do it 10 times and you are getting the same value, that means you have that much of confidence on your value, right? So probability of getting 50% of it increases with increasing n. The next question that we had in the assignment was thermodynamic equilibrium refers to. So what happens at thermodynamic equilibrium, right? As I said in that coin toss example, as I increase the number of coin, I go to equilibrium distribution. That means that equilibrium distribution is something which tells you about the most probable distribution. We must have seen You must have seen in the class that while defining the equilibrium, we wanted to maximize W. So that maximization of W was basically telling most probable distribution. It is having higher probability. That means that event, if I want to happen, the probability is high. And for any system, if I just leave it as it is, it will always go into the equilibrium. That means it will always want to increase the W and make it to the maximum value. For example, if I am having only oil in a beaker, and if I am having water here, the number of ways will be, for example, W1 here, W2 here, right? If I mix oil and water, then what will happen? Number of ways will be W1 into W2. What is happening? The number of ways have multiplied. That means the W has increased, and maximization of W will be there at the end. So that maximization basically corresponds to the state of thermodynamic equilibrium. So it is a most probable distribution where we see, when we are having an isolated system, entropy increases, right? Delta S is greater than 0, and that increase in entropy corresponds to decrease in energy. This we have seen, right, in the, I believe, week 2, using delta S of the system plus delta S of the surrounding is greater than or equal to 0, right? So instead of surrounding, we represented everything in terms of system. So we had delta S of the system plus delta U divided by some value, and then we had shown the maximization of entropy in closed system, that is NVT, for example, corresponds to minimization of energy. So entropy increases, energy decreases. So is there any option? It says maximization of energy, which is not the case, and minimization of entropy, which is also wrong. So that's why the thermodynamic equilibriums refers to the most probable distribution, where the number of ways in which I can distribute the energy is high, right? So this is question number 8. Now again, the question is on distribution of energies. Energy distribution in molecular system. There we saw, okay, for example, I am having m quanta of energy, and I want to distribute among n particles, similar to m chocolates I want to distribute in n students, right? So how to get the number of ways? W is equals to n factorial divided by n naught factorial n1 factorial. For this also the proof is there in the recorded lecture, n2 factorial and so on, right? So what is n? N is the total energy, right? Total okay, so m is the total energy and n is the total number of particles. So how many particles are there? Three particles. So n is equals to capital N, which is equals to 3. Now I want to distribute 5 quantas of energy among 3 particles. So particle may get 0 energy, 1 energy, 2 energy, right? So n naught is number of particle with 0 energy, n1 is number of particle with 1 energy. Number of particles with E is equals to 0, that is energy is 0, energy E0 I should say, and then E1 and so on, right? So n1, n2 particles can have 2 energy, n3 and 4, right? That means number of particles with energy 4, it is possible, right? Or number of particles with energy 5, that means all 5 quanta will go to only one particle, because we have 5 quanta, that is maximum value. But the question says that I want to distribute among 3 particles, and one particle gets 4 quanta of energy. So if one particle gets 4 quanta of energy, that means number of particle with energy equal to 4 is equals to 1, right? Only one student will get. If one student get 4, now I have only one quanta that is left, because total is 5. So that will be given to any one student. That means number of students with one energy equal to 1 will be equal to 1, right? And number of particles with energy 0 will be also equal to 1, because total number of particles are 3. One particle, one particle, one particle, so total 3 particles are there. You just need to substitute this value over here and you will get W is equals to 3 factorial divided by all these values, 1 factorial, 1 factorial, 1 factorial, and then you can see this is coming out to be, check the value, 3 into 2 divided by 1, so it is equals to 6. So number of ways in which you can give or substitute, give this 5 quanta of energy among 3 particles is equal to 6. You can distribute say in some other way. For example, you can give 2 quanta of energy to one, 2 quanta to other, and 1 quanta to the last one, right? That could also be the way. You can give 5 quanta to one particle, 0 quanta to other, but then there is only you, and then you calculate W, and then you will realize that W for that system will be lesser. So in equilibrium, almost all particle will be having some sort of equilibrium distribution, and that energy value of each particle will be close to the average value. It's not exact average value, it's close to that average value. Some might have some higher value than average, some might have lower value than average, right? And you calculate the W, and W will tell you what is the probability of that state to exist, right? And that's why this is something which gives you the equilibrium. Equilibrium means maximization of W. Then there is a last question for session. What is that last question? It says Boltzmann distribution, right? The way that we had seen, okay, how energy is distributed, and I had shown, okay, you can have various sort of distribution that are possible, but how this distribution is being governed. So this is one distribution. I can have n naught equal to 1, n2 equal to some value, and then that will be another distribution, right? Based on how I'm distributing the energy, I'll be having multiple distribution. Now how this distribution is decided? So it is decided based on Boltzmann distribution, which tells you what is the probability of a molecule to exist in that particular state. So the formula was Nj divided by Ni, where Nj tells you how many particles are there in jth energy level, which is higher than ith level energy level. This formula was exponential 1 by t1, 1 by minus 1 by, no, it was delta E by kBt. and delta E is something which is given as ej minus of ej minus of ei, right? So what does it tell? This is minus of delta E, minus of delta E, correct? So this delta E, there are two factors, one is temperature and second is energy. So if energy is higher, if energy is higher, for example, I have a solid, this mouse I am showing you here, this is a solid material, right? Why the particles of the solid are not moving at room temperature? They are connected to each other, they are adsorbed, they are attached to each other, they are not moving like gas particle. Why? Because their delta E is very high. Delta is attraction between particles is very high than the thermal energy kbt. That's why this ratio will tell whether it will go into that particular state or not. So there is always balance of thermal energy versus attraction energy. And whenever I'm having a gas particle, if I give small thermal energy, it will move, right? Why? Because the thermal energy and interaction energy, there is a ratio that we need to take. So in those cases, delta E is lesser than kbt. Kbt is high. So if kbt is high, then this ratio will be less, correct? Ratio will be, so depending on the delta in kbt, you can get the value of whether the state is possible or not. That means solid to liquid transition or liquid to gas transition and all that you can study using this. But when it comes to an isolated system, we just saw this for the sake of energy distribution, and there we saw, okay, at high temperature, the difference in energy level, right? The difference in energy between multiple level decreases, and because of that decrease, more and more higher level energy levels are occupied. That means with increasing temperature, higher energy levels occupancy was increasing. So answer was B, increases. You just need to substitute the value of temperature and you will get to know what is the probability, right? So this was about questions that we had in assignment 1. This we had discussed, right? And we will meet in next class to discuss the next assignment that will be in next week on Tuesday 6 o'clock. Okay, so that's all for today's class, that we had discussed these questions. So if there are no any more doubts, then we can close the session. Thank you guys for joining.